So this is on page 32, I believe. Can somebody just confirm that I got the page number right?
Yeah.
Okay, good. Thank you. So this deals with what's called Hooke's law and elastic potential energy. Hooke's law is going to be the basis of the lab exam you have tomorrow. Okay? There is a property that springs have that we're going to learn about, and basically the property tells you how stretchy or non-stretchy a spring is. So if I were to take a look at this spring, it has a certain stretchiness to it. If I were to take a look at this spring, it has a different stretchiness to it. Ouch. Okay? It has a different stretchiness to it. This one's really kind of loose, and this one is not as loose. If you look at the springs that are inside of shock absorbers or struts in vehicles, they're very, very stiff, but they still are stretchy. They're stretchy in kind of a compressive way, and springs can either be stretched or compressed depending on how they're designed. Anyway, Hooke's law is something that's going to explain in one way how stretchy or not stretchy a spring is. And there's a better word for that we'll get to later. Okay? And we're also going to be using that to learn about elastic potential energy, because this unit, everybody, is all about energy. Well, it's about circular motion, and it's also about energy. All right? Fair number of years ago, what are we looking at? 350 years? Approximately 350 years ago, Robert Hooke, an English physicist, showed that the stretch produced by a force applied to a spring is proportional to the magnitude of the force. What does that mean? Let's unpack that. If two things are proportional, and you can sketch this somewhere if you like. There's even a grid there, isn't there? Didn't I provide a little? No, but you can put a little grid there. If two things are proportional to each other, then that means graphically the relationship between the two quantities looks like that. So, we've talked about this before when we learned about Newton's universal law of gravitation. Proportionalities exist because when you double one quantity, the other doubles. When you triple one quantity, the other doubles. And I don't know if I use this illustration. I don't think you need to or want to write what I'm going to just write right now. Don't. But, you could have number of liters of gas and cost. That would be a direct proportionality. That would mean that if you purchase a certain number of liters and you pay a certain amount, if you could go back in time and purchase 3 times as many liters, you would have ended up paying 3 times as much. The thing that's going to be strange here is that we're used to this proportionality producing a graph that goes through the origin, but it may not go through the origin. And it might not go through the origin not because of any kind of experimental error, but there might be a physical reason why, depending on what you plot, the graph looks like this or like this. But we're going to put it through the origin. And unpacking this statement, he's saying that the stretch produced is proportional to the magnitude of the force. I'm going to turn that around, and I hope this makes sense to you, that if I say the number of dollars you pay is proportional to the number of liters, I could say the number of liters is proportional to the number of dollars, that they're proportional to each other. And I'm going to choose to put this x down here. This is the variable we're going to use. And this x is the stretch produced. It's a distance. So, for example, if I take a look at this spring in this state, and I just say that, well, that red marker is at my nose, if I stand up nice and straight instead of slouching, and then I look at it here, the amount of the stretch would be the distance from my nose to where it is now, maybe 8 centimeters, 10 centimeters. So that's an actual distance, and we're going to be using x as that distance, but we're going to say it's a displacement. And this is the amount of force, and it is also a vector, although, well, I'm going to put vector symbols around both of these, but I'm going to do this because it turns out that even though there are vectors involved, we don't normally consider the direction. And you'll see why as this lesson unfolds. And this force is sometimes called Fs, a spring force. And in the case of what I'm looking at right here, the spring force is actually a force pulling up on the mass. It will be important for later, and there's a lot of moving parts to this lesson. But we can get away with just saying that the force that the spring exerts on the mass, which is up, is the force of gravity pulling down on this mass. So in this particular case, and I'm trying to help you out for your lab exam tomorrow, if you took this mass times 9.81, you would get the applied force. And if you took the distance from where it was to where it is, you would get x, and you could have an ordered pair that you could plot on a graph. Are you with me on that? And then, I don't know, I think this is 200 grams. Then if you wanted, you could put 500 grams on your spring and measure from where it was to where it stretches. Now think about this for a second on what Robert Hooke is saying. Can you do me a favor and figure out how many times larger 500 grams is compared to 200 grams? 2.5 times larger. So if I were to measure, and we're not going to do this because you're going to do a lab tomorrow. If I were to measure the displacement from where this red marker starts to here, whatever that is, and then I were to put 500 grams on and measure the distance from where it lands to where it started, this distance should be 2.5 times greater. And it looks pretty close, doesn't it? I mean, we didn't measure it, but I mean, just using your memory of those distances we saw, it looks pretty close. This is what Hooke's law that this guy developed says, that the greater the force you apply, the more the stretch is. So that's what the proportionality means. And again, it's so much easier for me to talk about the force being applied to the spring as being the force of gravity of an object hanging on a spring. Although it doesn't have to be. It can be a horizontal spring that's oscillating or that has some mass on it. So this is what it's saying. Okay, we use symbols for this, but this is what Hooke's law is saying. Now, we have some details here, and I don't have the absolute value signs around this because this is how it appears on your formula sheet. If you were to look at your formula sheet, you will find this formula under kinematics. And I understand why it's written the way it is, but I think it can be confusing unless I explain to you what's the deal with the negative. So these are vectors. Fs is a force that's a vector, and x is a displacement, which is a vector. But look very carefully at about what it's telling you that Fs is. It's the force that the spring exerts on the mass. So look at this situation right here. This is actually 5 newtons. It's 0.5 kilograms times 9.81 meters per second squared, or newtons per kilogram. The weight of this mass is 5 newtons, and that's why I've got that on there, so you can see it as a force. And that force of gravity is pulling down, and right now, for the most part, everything is in static equilibrium. There's always going to be some spin with springs because of the nature of the twist. But this red marker on the spring is experiencing balanced forces. Which means if this mass is being pulled down with 5 newtons, and it's pulling the marker down with 5 newtons, something must be pulling the marker up with 5 newtons. What is pulling the marker up with 5 newtons to balance the force of gravity? So let me draw this. We've got our spring, and on the end of the spring we have a mass, and there's a force of gravity acting down on the mass. And you know what? Forget about the red marker. There is a force of gravity acting down on the mass, correct? The mass is not experiencing any acceleration, so the forces must be balanced. My question is, what's the force that's balancing that force due to gravity? There has to be something. What is it? Hunter. The force applied by the spring. So this is the force applied by the spring. It's up. Now, the force applied by the spring to this mass is up. What's the displacement of the mass? Well, or the displacement of the spring. It goes from this position to this position. The displacement is down. So the displacement is negative and Fs is positive. And no matter what happens when you have a mass on a spring or a force being applied to a spring, the force that the spring exerts on the mass will always be opposite to the displacement. So if I have a spring laying horizontally and I stretch the spring to the right, the spring wants to pull the mass back to the left. And that's all this negative is there for, is to tell you that if you want to look at vectors, the force that the spring exerts on the mass is always in the negative direction compared to the displacement of the mass on the spring. And if you even take a spring, and I don't want to get into too much detail with this today, but we take a spring, and it is the type of spring, and I will show you one, and it could be laying horizontally or vertically, it doesn't matter. We take a spring like this one. Would you agree that I can apply a force to this to stretch it? Okay, well, when I do, look at my thumb at the bottom, I'm applying a force downward. The displacement of my thumb is negative, but the spring is pulling back up, opposite. I can also take and apply a force upward and squeeze the spring, and it's going to want to spring back down. So when I apply a force upward, I'm creating a positive displacement, but the spring is pushing in a negative direction. So if I pull it this way, the spring wants to pull back. If I squeeze it this way, the spring wants to push back. It's always pushing or pulling in an opposite direction. So that is the only reason why we have that negative. And in this unit and course, whenever I talk about Hooke's law, I will always just say F equals kx. Because you know what? Sometimes I want to talk about the force applied and not the force that the spring exerts. Any questions about that formula? Okay. Describe how the force applied changes the amount by which the spring stretches. Well, we're just going to write this out officially mathematically. The force applied is proportional to the displacement, or the distance it stretches. But what this means, and we're going to go around in a circle here. Okay? I've already told you what Hooke's law is. It's a formula. F equals kx. But if two things are proportionality, if two things have a proportionality, that means we can create an equation by finding a constant of proportionality that's a long word, and multiplying the constant of proportionality by the other variable. Right, just to give you an illustration of what I'm talking about, the cost of gas at the pump is related to the number of liters, and the constant of proportionality might be this number, because that's how much it is per liter. I mean, there's a number that connects these two. But just like if I go to a different gas station, this number might change. If I go to a different spring, nope. I want to use a mass and a spring that don't result in it ruining the spring, which I think I just did with that other spring. This one's going to be close. Should be wearing eye protection. That's the same input. That's the same number of liters, but look at the cost. The cost is different. You understand this isn't really liters in cost, right? It's the same applied force, but look at the displacement. So the constant of proportionality of this spring must be different than the constant of proportionality of this spring. And you can tell that this spring that I used has been damaged. Do you see how the coil is different on one side of it? Not a big deal. Okay? Overall, you wouldn't notice once it stretches to a certain point. And I say that because tomorrow in your lab, you might have a spring that looks a little bit different in one place than another. It doesn't affect the overall spring constant. So the constant of proportionality here of a spring is something that tells you about the spring. And I will just tell you right now that the constant of proportionality of, say, this spring is greater than the constant of proportionality of this spring. Because this spring requires more force to stretch it a certain distance, the constant of proportionality is greater. You want to stretch it this much, you've got to apply a large force. That larger force times this displacement gives you, that larger constant of proportionality times the displacement explains the larger force. So that's the description. In the formula shown, Fs is the force that the spring exerts, y the negative sign in the equation. We've already talked about this. It's because the force that the spring exerts is opposite to the displacement of the spring. And I don't, honestly, I don't really care too much if you truly understand that. But anytime we write this formula down, even if I put S or if I put applied or whatever, anytime somebody says, well, why don't we have a negative, I'm going to say because of this. So I feel as though if I cover this once or twice, you know we don't have to worry about the negative. So there's the formula on your formula sheet. That's how I would prefer to write it. In fact, I will write it like that most times. All right, warm-up number 1. In an experiment to test Hooke's law, and by the way, Hooke's law is about forces, and we want to talk today about energy. We're only learning about Hooke's law here so we can learn about elastic potential energy. In an experiment to test Hooke's law, students suspend a series of masses from a spring and measure the position for each mass. This looks suspiciously like what I'm going to expect you to do tomorrow. Okay, all of these springs that are tucked into the ceiling will be released, and they will be hanging by strings. And your job, given a number of masses, is to do a lab where you determine the constant of proportionality. Maybe I should back up here. This K is the constant of proportionality. It is what we call the spring constant. Okay, we'll get back to that in a second. So the question is, verify Hooke's law by plotting a graph of the force exerted versus the position of the mass using the plot features of your calculator. So, you know, it's 2023. Let's not worry about getting a sheet of graph paper while we're learning. We can put this into our calculator. It's been a while. You go stat edit. And it's very important for you to know that you would never, ever use this as a data point. It's not a data point because it's not something that's measured. Okay, so you never use the origin as a data point. Now, why do we have 3 columns here? Well, if you were to do this lab tomorrow and you take a mass of 200 grams and you put it on here and you measure the displacement. Let me turn this around. And you measure the displacement from where it starts to where it ends, however you're going to do that, and your springs will not have little red markers on there. And you measure that, that's going to go on the horizontal axis, but you need to put the force on the vertical axis. If this is 200 newtons, how do we convert that to an applied force? Well, we find the weight of it. You multiply by 9.81. And that's all that's happened here, is somebody has taken the mass and they've multiplied by g in order to get the weight. So this is going to be our x, and I mean that in every sense of the word. It's x in the equation and it's x on the graph. And this is going to be our y. I don't know if you remember, I hope you do, but we always want to put our x's in list 1. Does anybody have numbers already in your lists? Okay, if you want to get rid of them, rather than delete, 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 you go to memory management, which is second plus. This is where you would go to reset your calculator memory. You take a look at all of your options and you go, well, this looks like maybe what I'm after. Clear all lists. And we go enter. It kicks us into the home screen, but you hit enter again and it says done. So now when you go stat, enter, that's what we get, an empty set of lists. So I'm going to put 1.96, 3.92, 5.87, 7.85, and 9.81. When we do labs, you might remember that I've said 8 points is the ideal number of data points. So when you do a lab tomorrow, we don't want just 5 or 6. Can you confirm that these are the same numbers on your handout? Okay. Take a minute and double check. 1.96, 3.92, 5.87, 7.85, and 9.81. And for L2, we're going to put 0.05. Well, I got them in, just after saying X goes in L1, I put them in the wrong place. Show you a trick here. If I quit out of here, I can access L1 by going second 1. And I meant to put it in L2, didn't I? So I can go store as L2. I could retype them all, but I just had my brain seized up there. And I said, you know, X has to go in list 1, and then I went and put Y in list 1. So now I'm going to put my X's, which is 0.05 in list 1, 0.099, 0.146, 0.197, and 0.245, and double check everything. I think it looks okay. So what we want to do is take a look at the graph. Now, I admit this is just made up data on paper, but you'll have to trust me that it's valid. The only problem is normally when you go graph, it's because you've put something in for y. So that's the first thing you want to make sure is there's nothing that you have in there for y. Maybe from a math class or from some other course. So I'm going to clear that out. And it has been a while, I understand that. If I were to go graph, I'm not going to see anything, and there are a couple of reasons. One of the reasons is I need to go to my window settings and set up my window settings to reflect this data. So my x goes from nothing up to 0.245. So I want to have a minimum x from 0 to 0.245, but I like to have some cushion room on both sides. So instead of going up to 0.245, I might go up to 0.3. And I might start at negative 0.1. You know what I don't like? I don't like the axes crowded right on the edge of your screen. I like it shifted over a bit. And my y's go up to, let's call it 10, maybe even 11. And maybe I'll go from negative 1 to 11. I am sure we've talked about this before, but does anybody remember or know what the scale is or does? Maybe we haven't talked about it. I think we have, yeah. It's just where the ticks are. So if I go from negative 0.1 to 0.3 with a scale of 1, I'm not even going to see any ticks. You might go 0.05. So you're going to see a tick at 0.05, at 0.1, at 0.15, at 0.2. And down here, I think a scale of 1 is fine, but I'm going to change it to 2. So after all that, I still don't see anything. Does anybody remember why? We will later, but that's still not going to show us the graph. Hunter?
Yeah, stat plot.
Right. So when you want a graph in math y equals, you just enter something for y, and you don't have to tell the calculator, oh, by the way, plot it. But when you enter data, you have to turn on a stat plot. If you look, when you go y equals, there's plot 1, plot 2, plot, etc. And there are a couple of ways to turn it on. You can just scroll up here and hit enter. And it's on. But I'm going to hit enter again to turn it off. I think it's better if you go second y and go into plot 1 so you can make sure all the settings are right. There's a default that's used. That means it automatically goes to it. That it's going to use your list 1 as x, which is why I told you to put x in list 1. So we turn it on, and this is what we want. And I prefer the mark to be a little square. If you use a dot, sometimes they're pretty tiny, and I don't like the pluses. So now when I do this, I get that. So the point is this. Is it linear? Does that look linear to you? Okay. Well, that's what Hooke's law is saying, is that line should be straight. The line of best fit needs to be straight. So we've verified Hooke's law. Sketch the graph below. Well, I don't know. Have you got a little grid you can sketch it on? No? So just a little... It doesn't have to be, you don't have to break out the drafting tools here. We just want to communicate on our note package that we are getting a straight line. By the way, just a side note here, you'll notice that this is bouncing up and down. What we will learn in the next unit is if I get this in oscillation and I measure the time it takes to go from here back to here, it's going to maintain that time. Even if we look back in 15 minutes and it's only going up and down this much, it will still take the same period of time to go up and down, as long as it's not acting like a pendulum at the same time, which is what it's doing here. This is kind of a combination between a pendulum and a bouncing spring. Okay? But the time it takes for a spring to go up and down is an important feature of the spring as well. And the mass on it. So there we go. We're done. What else are we asked to do? Find the slope of the graph. This is where we do the linear regression. Okay. So we quit out of here, and you go Stat, Calc, and choose linear regression. And on my calculator, and probably most of your calculators, when you hit enter, you have to click through a whole bunch of options. If you have a TI-83 or certain TI-84s with a certain operating system, you don't. But this is just confirming all of that information. So what is the slope? The slope is 40. Right? The slope in y equals ax plus b is a. It's the number in front of x. So the slope is 40. 40 what? 40 bananas? $40 per liter? You know, Christina?
Newtons per meters?
Newtons per meter is right. And this is the spring constant. Because, and again, I'm trying to lead up to your lab work tomorrow. Because this line is essentially that. I know there is a y-intercept here, but let's not talk about it today. Or now, anyway. I know that that's the equation of the line. I can even show it to you on here. Don't worry about what I'm doing. I could have written down the equation I got and then typed it in, but there's a place you can access it. So when I take a look at this, it's pretty much y equals mx, isn't it? From a math standpoint. But force equals kx. So if the displacement is plotted on the horizontal axis and the force is plotted on the vertical axis, then it makes sense that the slope of the line is equal to the spring constant. This is how we justify that the slope is k. We don't say because k is f over x. You don't do that. You just compare y to y, x to x, and m to m. So the meaning of it is this spring requires 40 newtons of force to stretch it 1 meter. I hope you understand that if I take where did it go? It's such a tiny little thing. Well, it's gone. So I will take this one. If I take this and I stretch it 1 meter, well, I'm not going to go 1 meter. It's obviously a different spring now, right? So there is a certain range of displacements that are allowed before you change the spring constant. This would have a different spring constant. And it explains why I have a whole bunch of these, because every time I teach this course, I ruin another spring. So the important thing here is when you do your lab tomorrow, don't hang a 5 kilogram mass from the spring. Right? All right. So that's Hooke's law, bottom line. Now, the only reason we're doing Hooke's law here at this point in time is so we can learn about elastic potential energy. Would you agree that there is potential energy stored in this spring right now? Why? Because if I let it go, everybody okay? Because if I let it go, it does work. It did work to the ceiling. It would have done work to my eye if it hit me in the eye. But there was potential energy there. But it's not because gravity is doing something to it as it falls. It's because the spring is doing something to it as it releases. So there's something called spring potential energy. I want everybody to imagine. Did anybody do archery? Okay. So in archery, and you guys can attest to this, if I put my bow, arrow in the bow and I start to draw it back, when I draw it back this much, it requires a certain force to hold it there, doesn't it? But when I draw it back this far, it requires more force. That's Hooke's law. That's Hooke's law. The more you pull it back, the more it pulls forward. The displacement and the force are proportional to each other. So we want to sketch a graph here showing the force as I draw the arrow back a total distance of 20 centimeters. So we can label on here 0.2 meters. We should label this as x in meters. And there's some force. Well, let's label this as the force, and I'm not worried about whether it's positive or negative. It's just a force. What will this graph look like? Well, look like that. Now, just a second here. If I take an object, a 1 kilogram mass, and I apply a force to it to move it to this position, I've done work, correct? Where is the work, which is a transfer of energy, where is the work currently stored? Potential energy, gravitational potential energy. And the force that I apply, and this is where things get different from what we're talking about, the force that I apply is the same everywhere, isn't it? I mean, we don't nitpick here and say, well, when the mass is here, it's further from the surface of the Earth, so there's less force involved, okay? It's essentially the same force everywhere. But with elastics and springs and bows, the force increases from nothing to a maximum. And when we found the work done in lifting an object, we just took the force of gravity times the displacement. We want to take the force times the displacement here, but the force is different everywhere. So, the archer does work to the system. Where is the energy stored? Potential energy of the bow arrow system. You can argue that there's potential energy in the bow, but I'm saying it's in the arrow as well, because if I let it go, the bow will do work to the arrow, giving the arrow kinetic energy. And however much work you did, when you release it, that's how much kinetic energy the arrow will get. Assuming no heat, which is a good assumption here. How would you find the work? So let's say that this number right here is the force required to hold it at that point. Work done is force times displacement. I want to maybe just add something to this. I think I will. Nowhere in this question do I tell you that force, do I? I'm going to say, and I'm going to change this for next time, that the force required is 70 newtons to hold it at that point. Okay? My question to you is the 70 newtons an applied force? Yes. But why can we not use 70 newtons in this formula? You know me, I'm challenging you to think here. Is 70 newtons an applied force? Yes. Why is it not the applied force? Noah. Say that again?
Would you have to, because as you draw it back, you're applying different forces as...
That's exactly what it is. Look, if you look at this graph and you say, I'm going to calculate the work done by using 70 newtons, when are you applying a force of 70 newtons? At that one point. Would you agree at some point in time you were applying a force of 0 newtons? So we certainly wouldn't use 0 for the applied force. What applied force would you use? What number for the number of newtons could we use that would give us the actual work done? And this is challenging because you've never run into a situation where the force is changing. You'd use the average force. you'd use 35 newtons. Oh, and some of you are saying, oh, I was going to say that. Yeah. You would use 35 newtons. And we're going to do this. So I'm actually going to calculate this. You would use 35 newtons times the 0.2 meters, which gives you, I think, 7 joules. Yeah? How's my math there? Okay, good. But, and this is evident based on the fact that most of you didn't know how to get that force. You weren't thinking about it that way. We've already learned how to find the work done. It's the area. It's the area. To find the work done here, you go area, which is a triangle, which means rather than doing this, which I'm never really going to want you to do, I wouldn't recommend using an average force. I would just say the work done is the area, which is 1/2 the base times the height, which is 1/2 times 0.2 meters times 70 newtons. And guess what that's going to give you? 7 joules. Yeah. It's half of 70. So let's go back to this graph. So I've said that that force at the top is 70 newtons. If I were to look at a force of 35 newtons, which is halfway between 70 and 0, that is the average force. Now this only works because it's a straight line. So 0 plus 70 divided by 2 gives you 35. But I want you to notice something. And working with an average is complicated and it's not obvious. It's not obvious. Do you agree that the answer to this question, which is the work, is the area of this triangle? We've learned that area of a force displacement graph is work. Okay. Would you also agree, though, that the area of this rectangle is the same as the area of that blue triangle? Because the blue triangle has this extra piece up here, and the rectangle has this extra piece here, and it all balances out. So that's the deeper reasoning of why using 35 newtons works. But once again, I do not want you to think in terms of average applied force. I want you to think in terms of this, okay, in terms of area. So how would you find the work? You'd find the area. Well, the work done then turns out to be this. Let me explain this because I put numbers in. If you go back to your graph and you want to do this in a general sense, this is x, and the force, according to Hooke's law, is kx. The force is kx. So if I want to find the area of this triangle, and I need to get rid of this other stuff now. If I want to find the area of this triangle, it's 1/2 the base, which is x, times the height, which is kx. It's 1/2 kx squared. And everything we've done today up to this point is simply done so that we can draw this conclusion. That now we have a new formula that can be used to calculate elastic potential energy of a spring or an elastic band or something that is stretchy. If I ever ask you to find the elastic potential energy or work done in this situation, you are not going to even look at a graph. You're simply going to go to the formula. So this is on your formula sheet under momentum and energy. Here's the formula for gravitational potential energy. Here's the formula for elastic. It's up to you to know which one is which. All right. 2 quick examples. A spring has a spring constant of 4 newtons per centimeter. That means if I want to stretch the spring 1 centimeter, It wouldn't be this spring, I'll tell you that much. If I want to stretch the spring 1 centimeter, it probably wouldn't even be this one. I need to apply 4 newtons of force. It's a fairly rigid spring. Bottom line is that's K. How much potential energy is stored in the system if I stretch it to 6 centimeters? Well, elastic potential energy is 1/2 kx squared, which is 1/2 times 4. Ooh. Except we have to use standard units. So 4 newtons per centimeter. We want to convert this to newtons per meter. So what's going to happen here is some of you will think centimeters to meters is divided by 100. And that's true. But we're not converting centimeters to meters. We're converting per centimeters to per meters. And if it takes 4 newtons to stretch it this much, then it's going to take 100 times more to stretch it a meter. So this is going to be 400 newtons per meter. Now we can put the numbers in. 1/2 times 400 newtons per meter times 0.06 meters squared. If you look at the units, everybody, we have newtons per meter, and we're multiplying by meters squared. One of these meters cancel, and you're left with Newton meters, which is the definition of a joule. I want to say 72. I'm obviously wrong. So 1/2 times 400, I want to say 72, times 0.06 squared, I'm wrong. Like 7.2 maybe? 0.72? 0.72. 0.72 joules of energy. That's it. What does that mean? It means that if this were a slingshot, and when we say springs and spring constants, it could be elastics. If this were a slingshot and I put a pebble in there and I pulled it back 6 centimeters and let it go, the pebble's going to end up getting 0.72 joules of kinetic energy. And number 2, a spring is stretched to a position 35 centimeters from its equilibrium position. All that means, if I go back to this situation, it doesn't matter. We're not using the red marker, okay? But see the bottom of this little ring? That's the equilibrium position. So if I say it's stretched to 35 centimeters below its equilibrium position, then that is the displacement. 35 centimeters is the displacement. So that's x. Which is, in meters, 0.35 meters. At that point, the force exerted by the spring is 10.5 newtons. What is the elastic potential energy? Well, it's 1/2 kx squared. How are we going to find K? No, not quite. Christina?
Well, for K, we need to 2 times the potential energy divided by x squared, like for the formula.
Except we don't know the potential energy. So I misled you a little bit there. I'm not saying how do you use this formula to find K. We want to use this formula to determine the potential energy stored in the system. But in order to do so, we need to know the spring constant, which we don't know. And this is a common, I don't know what that was. And this is a common thing that happens in high school physics is you have a formula you're going to use, but you have to take a detour to use a different formula to find something else first before you can use the first formula. So I'll ask the question again. How can we use the information in the question so that we can figure out what K is so we can calculate the potential energy? No.
S is equal to negative K times X, so you divide X by S.
Excellent. We're going to use Hooke's law. So 10.5 newtons is the force at that point in the stretch, equals K times 0.35. So we're going to divide the force at that point by 0.35 to get K. Then we're off and running and we can calculate the potential energy. So what do we have? 10.5 divided by 0.35. Oh, that worked out nice. K is 30. It's newtons per meter. Now we can put that in here and have 1/2 times 30 newtons per meter times 0.35 meters squared. Just like with your kinetic energy formula where you have that 1/2 mv squared, it's very easy for students to forget to square v. Don't forget to square your x. So I'm getting about 1.8 joules. About 1.8 joules. And just for confirmation, anybody else get it? Okay. Now, just put your pencils down for a second. Don't write anything I write on the board or anything I say here. I just want you to think about it. So this is what we did to solve this problem. And it's correct. Somebody comes along and says, well, I'm asked to determine the potential energy. The potential energy is the work done, and this student's statement so far is correct. And the work done is the force times the displacement, and they take 10.5 newtons times 0.35 meters, and they get what I want to say is 3.6 joules. Can you confirm that if you multiply those, it's 3.6-ish? That's wrong. What has this student done wrong? Their reasoning is perfectly valid. And I'm explaining this because some of you are going to do this by mistake from time to time. Ryan?
They didn't take the average.
Right. In this formula, not only is the force the applied force, but it's the average applied force. And when we say it's 10.5 newtons, that's the force the spring exerts at that displacement. It wasn't 10.5 newtons the whole time. So if you divide this by 2, you'll get the right answer. Or you could find the area of the graph. But my point is, why would you do any of that when you have a formula for potential energy? Even if the question said determine the work done, I would still use the potential energy formula. All right, so you've got about 15 minutes to try a few of these problems for tomorrow. Tomorrow you're going to be doing a lab. I'm not going to give you a lot of guidance. I'm not going to tell you a precise procedure. I'm going to tell you a general procedure, and I'm going to say you need to get to work on it. Any questions with that final example? All right. Get going, and I will come around in a few minutes just to help you out if you need it.